Hello, Bhavna, I'm audible.
Hello, sir. Yes.
Alright. Okay, so Bhavna, okay, Bhavna, so we have already completed the vectors chapter. Now we can move to the new chapter. Before that, do you have any queries from the vectors chapter? Any problem you're not able to solve or something?
So as of now, no. Like if I have any doubt, I'll be asking tomorrow.
So I think we can start the new chapter motion, right?
Yes, sir.
Now, the new chapter is kinematic. Okay, here we are going to do the study of motion. Study of motion. Okay, so we will basically study some kind of motion. Um, 1D motion in 1D. I can write this as motion in one dimension. So how many dimensions you have? 1, 2, and 3. Okay, 1D, 2D. The last one is 3D. Okay, so we will be discussing all the three different kind of motion. All right. Here, if I just talk about either you will be having X, Y, Z. Okay, motion will be either in three, either in three plane. Here, what happens is object generally follows a straight line path. In this, basically, object is in 2D, so you can say something like XY, YZ, and the last one is ZX. Okay, a vice versa will also follow. The third one is just XYZ, combination of all three. So you just have one case. Is this clear? So our main most of the topic of discussion will be just these two. Okay. Wait, yeah. This is the major part. This is the smallest part basically.
So motion in a plane is two-dimensional, right?
Yeah, this is part of motion in a plane. Okay.
Okay.
Basically, you can say this is a part of motion in a straight line. The first one, the motion in 1D, and the motion in 2D can be a part of your motion in a plane thing. Okay. All right. So let's move with the low motion in 1D. Just a second. A second. Look, we will try to understand all the concepts in motion in 1D such that we can like in when we will move shifting from one dimension to two or three dimension, we just have to change the dimension or understand how to apply it into the different dimensions. Okay. We will not go with how to go to the concepts in the different dimension. Concepts will remain same. Okay. You will be just getting added with a new dimension for these kind of things. Is that clear?
Yes.
All right. So, so, okay, so okay, so basically in motion on 1D, some topics we are supposed to study. First is frame of reference. Here we will be studying different kind of frame of reference. Okay. Rest of motion, position vector, displacement, uniform, non-uniform motion, accelerated motion. A little bit use of integration differentiation, which we have already studied in the mathematical part. So if you forget the differentiation integration, you can just go through that. Okay.
Okay.
We will be using here basic differentiation, basic integration, not some hard stuffs will be there. Okay, just an easy part. Okay, so let's start with the frame of reference first. I'll see how much very small part is there. Okay, so frame of reference. Basically, we have two types of frame of reference. One is inertial, another is non-inertial. Okay, it should be E inertial. We have two different kind of frame of reference. What are these frame of reference basically? A frame of reference which is either at state of rest or moving with a constant velocity. You can call that as an inertial frame of reference. Okay, so this reference can be called as a reference moving with a constant, or you can say a uniform motion. Okay. Bhavana, when I say a uniform motion, it means either a body is at the rest or either he is moving with a constant velocity. Okay. We have not studied the velocity part a lot, so you can just remember a term which is velocity. And to be a uniform motion, it should be having a uniform velocity. Okay. I can simply say
Ah,
that it suggests that you should be covering the same distance in the same amount of time. Okay. Um, for the example, I can simply say that if you are moving in a some straight line going, let's say you have to cover 10 meter. Okay. So for a uniform motion, whatever the distance you have covered in the 1 meter, like whatever the time you have taken to cover 1 meter, the same time you should be taking to cover another 1 meter, or you can say, like, for example, you took 1 second to cover 1 meter, so another 1 meter should be covered also in the 1 second, and this should be followed for the whole path. Is that clear?
yes,
All right. Basically, if I try to calculate speed at any instant, it should come out to be the same. Okay. That is the part where we say that it is a uniform motion. Okay. And in this particular case, when I talk about the non-inertial, you can have some acceleration. Frame of reference can have acceleration. Have some acceleration. Okay. These two are just a definition, but it does not explain a lot of things. Okay. How and where we should apply. So, what I can say. All right. Look, so if I just make a Cartesian plane, you can see that we have three types of Cartesian plane, right? X, Y, Z. All of them are perpendicular to each other. They also meet at some particular point. I can say O. Can I say this?
yes,
Okay. So when a particle moves in space, you can say its position at any particular time when you are going to check. Okay, can be calculated with the help of all these three dimensions. Understood? If I just try to make it over here, this is one dimension. This comes up with another dimension, and this comes up with the third dimension. Okay, and if I say the particle is currently at this particular point of instance, so I can try to calculate what is the position, right? And we have already studied very well what how like in the vector chapter how we can tell the how we can predict this position vector, right? I can simply say, okay, wait, let's make it change the color. Yeah, assume this is the point, so I can simply say you will be writing like assume a position vector is given to you as 2, 3, and this is the 4. Okay, this is given to you, and you know how we already know how to make this kind of thing, right? You just have to like start whatever you want. You can say first travel x direction. Okay? So you said okay, let's travel 2 meter in the x direction. Okay, then 3 meter in the y direction from the same point. Okay, 3 meter in the y direction you went. So this is 3 meter in the y direction. You can see, and after that, 4 meter in the z direction. So you can simply say this is the travel. This is the 4 meter I was supposed to travel with them. Rewards. Something around this kind of 4 meter in the x direction. So I can simply say this might be the point in the plane which represents 2, 3, 4. Is that clear? And if I just want to represent it with a vector, so this is the vector representing this particular point of instance. Clear, Bhavna?
Yes.
Any doubt till here?
No, sir.
Look, if you see the figure, it seems like this distance is smaller than all these three distances, right? But it is not actually because 3D figure is there and we are just like we only have our 2D like we have 2D plane, so it's a bit hard to visualize a 3D figure in a 2D plane, okay? Because this thing like basically this line is coming out of the plane towards you, like sitting. Assume you are having a laptop and the whole part is in the laptop and the this line is coming towards you, okay, out of the laptop. So that's the part where visualization comes up. Okay. See. All right. So let's move further. More of reference and all. Okay. For these two things, I will explain in a very simple way. Although it might not be an easy part in inertial and non-inertial. Sometimes we call that non-inertial frame of references are those which don't follow Newton's laws. Okay. Why they don't follow? Because of the acceleration associated with them. An inertial, we call them as the frame of reference where you can easily apply the Newton's laws of motion and it is applicable there also. Okay. In non-inertial, what happens is when you apply that, either the because it is in the acceleration, we apply it in a wrong manner. Okay. That is the part. You can simply think of it. You are moving with a train, okay, and the train is having acceleration because you can see the train's velocity changes with the time, right? Okay.
Yes.
So if I ask you, what is the speed of a tree outside? Okay. So with if you are because look, its speed is changing, so I can simply say currently you are in a what I can say you in non-inertial frame of reference. When I say frame of reference, is basically the point through which we are going to observe the whole world. Okay. I have 2 points right now. A stone at this point. It has zero acceleration, zero velocity. I can simply say this is inertial frame of reference. Okay. So if I want to calculate velocity of this tree, I will say it is zero, right? It is zero. The speed or velocity, whatever you want to talk about, it is zero for this tree. But
Yes.
with respect to this person, it won't be zero because if you ever have traveled even by any vehicle, it is bus, train, whatever, you must have noticed if you're moving with a train, you will see outside world moving away from you, right? In the behind direction as compared to you. Have you observed the
Yes.
same? All right. So assume this train has a velocity somewhere around 10 meter. Okay. So assume you're smart enough and you said that whatever this velocity, this is mine. This does not have a velocity. So you will say, okay, that is fine. I am able to see this moving this direction with 10 meter. This is what you are going to see, right? But if you subtract this 10 meter to 10 meter, you will get the zero. So you can see that this has a zero velocity. But the problem is there's something extra that is acceleration. It means here you said zero, but after some time your velocity gets increased to 20. Okay. So again we have to apply the same thing in a different manner. Are you getting a point? So that's why when you are in the accelerated motion or non-uniform motion, the frame of reference makes it harder for you to calculate the things or apply the Newton's laws of motion. Is that clear? In that cases, we will prefer to take a relative velocity concepts. Okay, that we'll study in the detail. Let's go to the first, to some what I can say introduction part. Okay, so we are done with the 1D, 2D, 3D. Just a simple introduction was there. In 1D, you can see our object is just moving in a straight path. Okay, motion along a straight path. In 2D, it's a motion in a plane where you can have a projectile motion, you can have a circular motion, so on, so on. In 3D motion, any object is moving in a space. Okay, in any random directions it can go. A random molecule of the gas molecule, right? Motion of a gas molecule, how it moves in random directions. It does not
Yes.
confine to move in a straight line or in a plane, right? It is able to move any whatever the direction you can see. Okay. So let's talk about rest and motion. So we have two states. Um, We have basically two states to talk about. One is rest, another is motion. Okay. In these two, you can like rest is rest. Okay, rest means object is not even moving or making any disturbance. Okay, in its position. That is fine. Just a single state. Motion can have different ways. How the body is in the motion. It can be uniform. It can be non-uniform. It started with motion, going into rest, again motion, so on, so on. Like different kind of aspects we can have with respect to the motion part of it. So yeah, I can very in a simple note, I can simply say that a body is to be at the rest when it does not change its position with the time. Okay,
Okay, sir.
a very simple note. I can simply say this rest when body does not changes its position with the time. Changes its position with the time. Okay. So basically, if I just try to follow a graph or something, okay, what does this mean? Assume you are starting at the rest. Okay, how I'm saying an object is at the rest or not? Let's say this is a point A and this is the point of B. Okay, and this is the distance between them. Assume a person came at time is equals to.
So you are
Uh,
writing anything on?
yeah, I have changed my page. Can you see this? Wait, let me see.
No, sir.
Wait a second. I'll just make you follow my screen. Maybe you can follow it within a minute or something. Can you see this now?
No, sir.
Okay, I'll just copy everything. Okay, I'm coming back to the first page. The problem is page get very lengthy. Like the length gets too much. Now can you see this? The rest in motion thing.
Yes, sir.
I have came back to the main page, okay, the first page. Look, so you will be just getting the single page, but it will be very long. Okay, so that is all right. So look, what I was saying is two like okay, this is the condition we are having A and B. Okay, this is the 2 points. The straight points are there. The some distance is there. Okay, assume a person or maybe you are the observer. Okay, who is going to observe the things. So assume this is the well, it's not selecting the pen. All right. So you see, I can simply say when you observe the time t is equals to 0, the position was here. Okay. After some time you came and said, let's check it where you are right now. Currently the time has been passed by 1 hour. You are still at the same point. You are still at the same point. Let's say this is position P. Okay, I will represent this is position P1. Okay, so here you can say you had a position P1. After 1 hour, you are still at the P. Okay, so you can see you have not changed your position. Can I say this? This is a state of rest.
Yes, sir.
I'm not sure. Look, I can see. I look. I have only observed for 1 hour, so I can say you are at the rest in just for this 1 hour. Okay, assume After 1 hour, let's say I came at time t is equals to 1.5 hour. Okay, this 1.5 hour is not with respect to this 1 hour. Okay, it is with respect to the time when I started the zero. Okay, so when I say
Okay.
1.5 hour, it means from this zero, the time has been passed by 1.5 hour.
Okay, sir.
Now what I'm able to see that now the position is P2. Okay, all right. I can simply say this part is having a motion. This part had some motion. Okay. So here let's say time t is equals to 0. T is equals to 1.5. Okay. No, just 1. At at t is equals to 1.5, where you are, I can say this is P2. So what is the distance you have covered? I can simply say this distance, right? So the distance you have covered it.
Even repeat.
What happened?
The distance, sir.
Yeah, distance. Okay, so this is you can say nothing but a change in position. Okay, change in actual position. Okay, path, whatever you have taken, and the like whatever it is. Okay, so I can simply say change in position. Although this change in position does not make a lot of sense. Okay, because when I say you have just distance is just change in position, so it does not make a lot of sense. Okay, we will see why. Assume I give you this kind of path. Okay, you have started from here and you have ended up here. When I say just a change in position, if I just do the change in position, my change in position is just this part, right? But this is not my distance. My distance is the whole thing. Each path, okay, which I have covered.
Okay.
So you can say complete path between change in position. Okay? Where your position has been changed, complete path you traveled. Complete path, I think. Okay. Complete path you can say traveled by a body. Okay. Which kind of motion it was? Even the body was moving or not? As rest or whatever it is. What kind of motion it was?
Okay.
Yeah, one dimension motion. Okay. Okay. So look, always when we are measuring the distance and all, we have to talk about something called a reference frame. Okay. Understood. A reference frame is a point from where we are going to observe it. How we are going to observe it? Assume again the same point I'll take. Let's say person one is here, person one B is here. Okay. When you are sitting here, okay, and you move from here to here, so you can see that if I ask you where you have actually moved, in which direction you have actually moved. Let's say I'm saying just don't tell me which direction you have moved, just tell me where you moved, away or towards. Okay. So you can simply say for a person A, you have moved away from him. Can I say this?
Mm.
And opposite for the B, because for a person B, you have moved towards the B but away from the A. So this is a point where we have to keep track of the reference also. Okay, we have to observe, like we always need to care of the observer. Who is the observer? Okay. because for every object your motion may be different. How? Just assume you were traveling via this motion you covered via some train or bus, okay? And another person is sitting here. Now, look, for this person, this train had some motion. For this person also, this train had some motion. But if I ask you, what is your displacement with respect to train? Or what is the displacement of this train with respect to you? That is zero because look, if you see yourself, this was the bigger train, okay, and let's say this is the point where you are sitting. In the whole journey, you are sitting at this particular point itself, okay. So I can simply say motion of a train with respect to you or motion of a you with respect to train is zero, right? Because you have not changed position with respect to yourself. Is that clear? So this is the
Yes.
point where we have to keep track of the observer. Okay, understood. If we don't keep the track of observer, we will do the very silly mistakes. Because train was moving with 10 meter per second, and if I ask what is speed of the train, okay, with respect to you, I'm not asking what is the velocity with respect to a word. Okay, I'm asking with respect to you because you just know you have marked up that velocity is 10 meter. You will put the 10 meter, but not with respect to you. The velocity is zero. Okay, understood.
Okay, sir.
All right. So that's a part of a basic introduction with the motion in one dimension. Okay. Uh, one more kind of motion is there that is translatory and rotatory. I'll just discuss that thing and wrap up for today's. In the next class, we will discuss more of the position vector. Although we have studied that position vector, displacement vector, in the vectors itself. Just a small recap I'll give and move further. Okay. Velocity and lots of things we'll study here. So we have basically two kind of motion. One is translatory. Yeah, translatory motion. What kind of motion it is? Let's see. Your body is moving such way that the linear distance covered by each particle is same. Okay. What does this mean? Look, for a single point object, I can maybe okay. Assume for a single point object, because it is a very small object, so I can simply say if it has covered this path, so this is the path it has covered, right? But what about other bigger body? Bigger body means a rod. You are given a rod like this, and now I have to make it a motion. So assume I will just check the 2 points. Okay, although we can have multiple points, I'll be looking for 2 or 3 points. Let's say this is 1 point, this is 2 point, this is 3 point. I will try to observe this thing. So let's say this body, I let this body move from this position to um, yeah. I try to move this body. Yeah, assume you move your body from there to here at this particular point. So what is the path you travel? You can say that you travel each path, perfect path for each of the particles. What does this mean? Perfect path. Okay. Let's say for this one you have moved this path. Can I say that for this one also you have moved the similar path? Bhavana, can I say for this one also you have moved the similar path for all these three particles? It cannot be case that you have moved a different path for each of the particle of single body. Can I say this?
Yes.
Okay, so these are kind of translatory motion. Let's come up to different kind of motion that is rotatory. In rotatory, this is not true. Okay, rotatory. Assume this is a rod you have. Uh, okay, and this is a point with respect to which I am trying to rotate. So if you are aware of the motion, what kind of motion these does, so you can simply say if you were here right now and I have moved it from here to this particular point. So what is the displacement you have done? You can see for each point. Let's track it for each point. This is the one point, another point, another point, and this is the another point. Okay. Here also, this is the same point, another point, another point, and another point. You can see that distance between this point, the like distance traveled with this point, distance traveled by this point, distance traveled with this particular point, and distance traveled by this point is different. Can I say this?
Yes, sir.
Okay, so this can happen in case of a rotatory motion, but not in a translatory motion. Okay, there is something called trajectory. Trajectory is basically the path followed by a point during its motion. So whenever I say the trajectory, you can assume that the path followed by it. Okay,
Okay, sir.
okay. So in this case, what happened is the distance might be different, but the angle which has made, because you know the angle is same, right? Angle made by every person is still the same. Like if this is the theta, this is also the theta, this is also the theta, this is also the theta, right? Distance covered by each point might not be the same, but angle made by all these points with respect to this single origin point is still the same. Can I say this?
Yes, sir.
All right. So this is what your rotatory motion is all about. Any doubt? Any doubt till here?
No, sir.
All right, Bhavna. So this is all for today's class discussion. Okay. In the next class, we'll go more into the formula. Okay. How we have to solve
Okay,
and
sir.
all these things. All right. So I'll end the session by here.
Okay,
We'll
sir.
share the PPT, although this PPT does not have much information. But yeah, you can just take it as a reference and study more in a, like if you need some theory or something, you can go with by just get the name and study more theory about it. Okay, it will be better.
Okay, sir.
I will say because I have not studied, I have not taught you some more theory like numerical part or something. So you can just pick any textbook, whatever you have, and study from that as basic starting theory part. Okay,
Okay, sir.
all right. So Bhavna, yeah, that's all for today's class. Let's session. Bye.